In this video, we are going to build a machine learning model to predict activity of a person using smartphone sensors. This project is split into two parts, training a model and deploy it in smartphone. Before proceeding further, let's have a look at a structure of the dataset. The dataset is having 70 columns containing data from accelerometer, gyroscope, linear acceleration sensor and the magnetometer at a certain timestamps. The value from sensors were recorded by keeping the device in left pocket and right pocket, binded on wrist and so on. For the left pocket, there are 13 columns. First column is a timestamp at which the value from sensor were recorded. Then the 3 column for accelerometer reading, 3 for gyroscope, 3 for linear acceleration sensor and 3 for magnetometer. And the same order of sequence is repeated for every other method of recording. The last column in the dataset contains labels at each timestamp. Now let's start exploring it, but before that make sure you have Tensorflow version 1.13.1, both CPU and GPU version, Keras version 2.2, NumPy and Pandas. I am using Jupyter Notebook as an IDE, so let's start. Download the dataset from the link given in description and extract it into working directory. Now head over to the Jupyter Notebook and start writing code. Start by importing NumPy for linear algebra, Pandas for data manipulation, Matplotlib for data visualization and OS for operating system interaction. Set path to the dataset directory and see the files using listdir function. Now we don't need that readme.txt, so we will remove it. Read a CSV file using pandas read CSV function and make first row as a column for dataset. Use head function to see first 5 rows. Here you can see the last column, which is label corresponding to values. Now it's time to visualize accelerometer data of different activities to observe the difference in values. So by using matplotlib plot function to start plotting first 100 values in graph for different activities. First, for walking, plot x, y and z axis on the graph, and similarly do plot for standing, biking and jogging. Now look at all plotted graphs for different activities and it is clearly differentiable. The next step is to load all files into one data frame. Start by creating an empty data frame and iterate over all CSV files in the dataset directory and append them into above data frame. Now we have one giant dataset. Let's have a look at dataset. First, the data for different activities were recorded by keeping the device in left pocket, then they did same for the right pocket and by binding on wrist, on upper arm and on belt. We are going to use only left pocket and right pocket data because I know you are not gonna test this on binding your device on your upper arm or on your belt. Also, I am not including magnetometer data in the training dataset because majority of mid-range devices don't have magnetometer. So let's slice out left pocket and right pocket data from the data frame. For the left pocket data, we have to slice out from index 1 to 10, and for the right pocket data, we have to slice out from index 14 to 24, excluding timestamp and data of magnetometer in both the cases. Sorry, 15 to 24. But column names for right pocket data is different from left pocket data. So to make columns identical, assign left pocket column names to right pocket data and it's done. Now it's time to append right pocket data into left pocket data frame. And we can do this by using pandas concat function, and sort equals false will prevent shuffling during concatenation. And don't forget to concat labels of right and left pocket using same function where axis 0 means concatenation by rows and assign column name activity. Now we have same number of labels, so add these to training data in a new column name activity. And yes, it's done. Now we have our training data. Let's check how many unique labels we have. Here are 8 labels, but there is a typo in upstairs. So locate the typo in activity column in training data and assign correct label to it. Now we have 7 unique labels. Now split training data by slicing from 0 to 8th column and labels by slicing 9th column. Now we have training data and labels apart in xtrain and ytrain variable respectively. The labels is in string format and the training a model requires integer or float values because the data to be fit in model must be in numeric format. So convert them into integer values by fitting them into scikit-learn label encoder function. Now define a function to split train and test set. The default split size is 80% for training and 20% for test data. Now slice from 0 up to 80% of data in train X and labels in train Y, and rest 20% of data in test X and labels in test Y. Then return all variables. Now split the train and test data and verify the count of training and testing data and its labels. Output values from smartphone sensors are continuous and dependent on their timestamps, as we can see in the dataset and graph. It means you can't predict anything by just looking a single data point, because each value is dependent on its previous value. Continuous value can only be predicted by observing some values in a fixed window. But what does that mean? Let's see by this example. Suppose we have a model that can make predictions by taking continuous values as input, and it's already trained to classify these two outputs. Now we have a dataset to make prediction, so we can't feed only one point from dataset into model because it doesn't mean anything to it, and also we can't get anything appropriate by feeding whole dataset at once because that too doesn't mean anything. So to solve this, we can make a fixed size window and slide over the dataset. Now on first slide, it group n values and feed them into model. Then the model will correctly classify 0 because it's more likely to match with it. Similarly, on the second slide, it will output class 1 because of same reason. Continuous values are always dependent on some other value. In our problem, the value of sensors are sequential and dependent on time. This type of data is called time series data, so we have to solve this in the same way. We will define a window size and we will group values to make predictions. So to continue with this, first we have to convert our dataset into time series dataset. So to do that, import time series generator from Keras, define window size and number of features the dataset has. Now pass training data and labels in time series generator with the window size and batch size. Then do same for the test data and its labels. This function will convert the dataset into time series sequence during training. Please lower the batch size if you receive resource exhaust error. In neural networks, recurrent neural networks, or RNN for short, are best known network which remembers sequence of values over time. And a variation of recurrent neural network called LSTM, or long short term memory, capable of memorizing even longer sequence of values, and we are going to use this variation to make our neural network. So to do that, start by importing sequential from Keras, which is a linear stack of layers. Dense, which is a regular layer, contains feed-forward units. Flatten layer is used to convert n-dimensional vector into one-dimensional vector, and LSTM contains LSTM cells. L2 is a regularization function, and ADAM, or adaptive momentum, which will perform gradient descent or as an optimizer for our neural network to converge. Now make a sequential model having first LSTM layer containing 32 LSTM units and will return sequences as it is as output by taking two-dimensional input, which is a group of 100 values from every input column. Use regularization function to prevent layer from overfitting and assign a name to the layer. Flatten layer will convert two-dimensional output from LSTM layer to one-dimensional input to the next layer. And the next layer is a regular feed-forward layer, contains rectified linear units with regularization function and a name assigned to it. This layer will take input from flattened layer and act as a classifier for the model. And the last layer of the network contains 7 softmax unit, which will throw out probability for each class depend on the input it gets from the previous layer. And I missed the equal between activation and ReLU in second layer. Use categorical cross entropy as a loss function and ADAM as a gradient descent to compile this model. Model checkpoint is a callback from Keras to save best performance model during training. Now fit the training data into model and use test data as validation with the callback. And the training is started now. It will take time, so I'm skipping it. I stopped training at third iteration because I got acceptable accuracy and model checkpoint saved best model for me. But you can go through more iteration to get more accurate model. Now import that saved model and move over to exporting it so that we can get a deployment model. So to export, import freeze graph and optimize for inference library from Tensorflow tools. Define input and output node name for model and use TensorFlow write graph function to save structure of model and use TensorFlow saver to save model checkpoint. Finally, use TensorFlow freeze graph function to get a protobuffer file which we will use in Android. Now we have everything is ready and it's time to deploy in Android device. The deployment requires a physical Android device, Android Studio and internet connection. Let's start. Open up Android Studio and make sure you have active internet connection. Start a new project. Select an empty activity. Set name of app and choose minimum SDK and click on finish. The time it takes to load project is depend on speed of your internet connection. When it's done, open up app level build Gradle in Gradle script and add TensorFlow dependency. After that, click sync now and wait until it successfully download TensorFlow library. Now, create an activity classifier class and load TensorFlow inference from TensorFlow library. Define TensorFlow inference which will run model on device. Define name of model, input node name, array of output nodes and main output node name. Define data input size on which we trained the model and number of output classes. Now initialize inference variable in constructor of this class and pass the path of model file in it, which will be in assets folder. Now it's time to write a function to run classifier and return probability for each class as output. Make an output sized array result to store probability for each class. Then feed the input data to input node of classifier and run classifier to output node. Now fetch the probabilities for each class and store them into result array and return results. Now go to your project folder where you trained your model and open up models folder and copy this protobuffer file and paste it into assets folder in Android Studio by renaming it to model.pv. Define permission in manifest to use accelerometer and gyroscope sensor. Now it's time to code main activity. It will handle user interface, input from sensors and feed them into activity classifier. Start by defining window size and 3 list for storing accelerometer data, 3 for gyroscopic data and 3 for linear acceleration sensor data. Define sensor manager to control sensors and instance for accelerometer, gyroscope and linear acceleration sensor. Define results array to store prediction and instance for activity classifier. Now initialize all list for accelerometer, gyroscope and linear acceleration sensor. Initialize sensor manager to use Android sensor services and initialize all sensors to sensor manager. Now initialize activity classifier and bind event listener for each sensor to read the flow of data from all sensors one by one in real time. This event listener gives us two functions. First, on sensor changed executes when the device switch from one sensor to another sensor in order to reuse. Second, on accuracy changed executes when sensor reports different accuracy in values. We don't need this function and we will only use sensor changed function. Now get the current sensor and if the data is coming from accelerometer then collect the XYZ values in their respective list. Or if it's gyroscope, store values in gyroscopes list. Or if it's linear acceleration sensor, then store values to its respective list. Now write a function to make prediction from these values. First, make a list to store sensor data. Then move to check if all lists having more values than window size. And if it is true, Then slice out values of window size or define a timestamp and store them into above data list. Do it for accelerometer, gyroscope and linear acceleration sensor. Now pass the data to classifier's predict probability function. But wait, we have to convert data list into an array. Let's write a function which will take list as input and output an array. First, initialize an array of size of list and iterate over each items in the list and store in above array. Finally, return array. Now we can use this function to pass data in classifier's predict probability function. Use log to read the output of model in Android Studio Logcat and make sure to clear all list after prediction. Don't forget to register sensor event listeners in onResume function and unregister in onDestroy function so that sensors will stop when app closes. Now plug in your device and hit compile and run. Wait for Gradle to finish and app to install in your device. When the app launches, open up Logcat in Android Studio and see the output of app. But the output is something array of weird numbers. Let's understand what it is. Let's take this sample from output. If you remember, we have 7 classes in our dataset in string format. And to train a model we have to convert them into numbers so that mathematical operations can be performed. So we encoded each unique labels into unique numbers. Now take a look at model's output layer, which is having 7 softmax units. Each unit will predict the probability of their respective class, and the unit having higher probability will be considered as output class. So in this case the output is jogging. Now let's make user interface to show this output on screen. Go to the activity main XML file and change constraint layout to linear layout. Now add a text view to show probability for first label. Give it an unique ID. Set text size a little more and larger and set text color. Now we have total 7 different classes to predict, so make 6 more text view for each class. When you're done, change orientation of linear layout to vertical to align text views vertically on screen. Now go to main activity Java file and define text views for each class. Make a function to initialize them all. Use findViewById function to attach each text view to its XML views by using their IDs. Now go to sensor changed function and use text view set text function to set predict probability values in text view after running classifier and before clearing data. Hit play button and wait for install. Now it's making prediction, but the values for probability are 64-bit float values. That's why it is showing in scientific notation. So let's round off these values to 2 decimal places for better understanding. Write a function that takes values and round them up to some decimal places. We use big decimal class setScale function to round values to target decimal place and return new float value. Now use this function to round off result values at 2 decimal places. Hit play button when you're done and wait for install. And yes, it's fine now. Now it's showing probability in 2 decimal places. And congrats! You have just got to know how you can train and deploy any type of neural network in an Android device all the way from scratch. Link for all source code for this project is in the description. But if you missed something, feel free to drop it in comments and don't forget to leave your feedback. Also, drop that topic that you want me to make videos on. Thanks for watching.